Good to see you guys.
Good to see you too.
I think we're ready to go.
Yeah.
Fantastic. So I thought, quickly we'll start with some introductions. We'll move into a little bit of where we kind of first met each other. I thought that might be I know we're all engineers, but we can introduce a human element to it if we choose. And then I know Kirk's put together kind of an interesting graphic for us to look at, and I wanted to just kind of get some, use it as a Rorschach test to peer into your psyche and the way that you mind.
There you go.
So with that, hello everybody. I'm John Barnes. I'm with Barnes Global Advisors, and we're excited to bring this first of a 3 series. The next one will be hosted by Laura Eli, looking at her favorite subject, directed energy deposition. We're going to talk about ostensibly sintering and its impacts on processing and powders, and then to, I guess, a lesser extent, binder jetting, and the other processes that use sintering, and basically how they differ from powder bed fusion, and with a positive view that, hey, these are both productive technologies, but they are different, and what's useful to think about with that. With that, Tyler, I'll turn it over to you.
Thank you, John. It's a pleasure to be here today. My name is Tyler LeBrun. I am a member of the technical staff at Sandia National Labs, but I have a broad history with the aerospace industry and also powder feedstock production for additive manufacturing applications. And I guess the human element I can bring in today is outside of the technical work I do, I'm also the educational co-chair for the San Francisco chapter of the American Alpine Club. So I'm very much trying to get in the mountains whenever I can.
Oh, very cool.
Kirk?
Oh, yeah. Hi, Kirk Rogers here. on the Barnes Global Advisors team along with John. I come to you today with 30 years experience playing with metal powders. And, in the last decade or so, a lot of that transitioned over into additive manufacturing one way or another. And in the last couple of years, we've been doing a good bit of engineering services work to help people industrialize additive manufacturing.
Yes, and that is, as Kirk says, he wears gray pants because then the metal powders don't show up on him. So that's how humidity to metal powders.
Yes.
I thought it would be interesting when we talk about like how we actually first met, because this industry is small, and you constantly run into somebody, or it's like 2 degrees of separation. So and this is a quick fun fact. So Kirk and I actually were roommates in grad school. We were the first 2 of 3 graduate students from Kevin Trumbull.
Yep. We
just found out that our third person has been working with the Secret Service. So
wow.
We hadn't heard from him for 25 years. Now we know why. So that's interesting, I will say. And so needless to say, our dynamic on the team is perhaps different than than the rest. And Tyler, we met, I believe we met mostly through your the AMS committee work on recycling, reuse, and all of the fun definitions that we misuse.
That's right.
in powders. But I felt like, when I first saw it, I think I was like, well, this could be painful. And then it was kind of interesting, but I suspect it was an exercise. I think it's rewards a person with patience.
Patience and fortitude. That's what it's taking so far.
That's it.
But it's, I think it's necessary work, foundational work, I would say.
Thank you.
Yeah, absolutely.
So that's how I think we met. Who wants to go next?
See, I remember John was an undergrad when I met him at Purdue, I think in MSc 230, something, Intro to Materials. I don't think I was the TA though that time. I think we were just in the same, and then you graduated into the same group. I met Tyler only through Manuscript Monday, so we've actually never met in person. So that does one bit of infamy is you get known on LinkedIn as one sort of thing. And I have no idea about the rest of Tyler, like the Alpine bit. That's very cool. Or the running bit until we chatted the other day.
Does he exist outside of Monday? Is that?
I don't know.
Apparently, yeah.
Yeah, I think that's describes it pretty well. I met John through the committee work, and that's kind of now also started to include Kirk as well, and some of the work that we're doing to describe metal powders for both LPBF and binder jetting. And so that's principally where I meet a lot of the new faces outside of the what feels like an infinitely deep well of names and faces on LinkedIn, but through the industry committees that I participate on outside of my current role and previous roles in the past. That's where I meet a lot of the people that I'm good friends with now, and do a lot of good work currently on the side, trying to kind of push things forward with the industry. So that's, I think John and Kirk are right there, and that's on the history for me at least.
And tell us about Manuscript Monday.
Okay.
What was? Did you lose a bet?
No.
There's good work out there that nobody's seeing.
So as I tell this, the face is probably going to turn red. No. So Manuscript Monday has just been my attempt to do something both creative and unique for my little corner of LinkedIn, and if I can remember to push the little flag when I go to post to Twitter as well. But basically, I'm doing my best to pull relevant and recent research, read through the accepted or published manuscript as it currently exists out and available for people to acquire, and then kind of give either a short synopsis that's relevant to the broader AM community, maybe if it's a tangentially related topic, but perhaps maybe do a little bit of how does this topic relate to me and my history, and where I can see this type of research being applied. So give people the accessibility to understand why this kind of research is important, both now and perhaps projecting into the future. So that's where Manuscript Monday kind of what it's serving now in the LinkedIn space. But it's just been something that I've been fun, and I liked how it sounded. So Manuscript Monday is now the day that I'm frantically trying to find, what am I going to post this evening? I'm running out of hours, and sometimes it's like, well, Manuscript Monday was yesterday, but today is Tuesday, and we're going to make up for yesterday. We're a little late. So, but that's what I like to do.
If it's helpful, I mean, to me, it's like, okay, all these things are peer reviewed. This one's been it's like going into, Blockbuster when that was a thing, or your bookstore. Tyler recommends
Editor's choice.
Editor's choice. Yep. Yeah. What's on the table at the end of the counter, right? That's ready to walk in. It's like, oh yeah, that one. Done.
That's right. That's right.
So I think we may be flattering you with a little bit of mimicry. So I was talking to Wayne King on our team, and he loves a good scientific paper. So I said, you need to do Wayne's World, So, one paper a month, and go talk to the author and, kind of dig into it a little bit.
Yeah, he's a good person for that.
The details.
Yeah.
I will say Chelsea's coming up. She's very on brand. She's come up with 2 minutes of tech with Chelsea. So look for that, everybody.
Yeah.
We're now committing her to that.
Welcome, Chelsea.
She just recoiled in horror, I thought. I will say, just for the audience, go ahead if you have questions or things you want us to look at, put it in the chat, and we will, we'll try to address those questions, etc.
Okay.
So, right before we get to the opening slides, we're going to tease this up a little bit. One of the things I wanted to get to was what interested you about doing this topic. There's a lot of things you could be doing, and other than me being moderately convincing, but perhaps not the reason why you're doing it. What's interesting to you about it? I think I've been looking forward to it because it was like an opportunity to really dig into, some really potentially prominent details, because I believe strongly in these processes. But if you don't understand how they work, you're probably going to make a lot of mistakes that you don't necessarily need to.
There you go.
Mm-hmm.
So, for my rationale, the thought was, if I'm an engineer at a company, this is the conversation that I want to be in on. because then I'm going to look super smart when I have to write a spec.
Yeah.
Or I write up a call point. Tyler, what was intriguing to you about the topic?
Well, I think this topic is really touching on an area of additive manufacturing that powder bed fusion has kind of taken the spotlight for quite some time. And so there just hasn't been the industry attention that I would like to see from my little corner of the world on what the potential benefits and application cases are for binder jetting. And people that have only ever lived in the LPBF world probably don't have an appreciation for what those idiosyncrasies are that make it different, to what you were just saying, John, about really how can you avoid the mistakes early on so you can get the most utility out of it as quickly as possible. So how does the process differ? How does the science differ? What do you have to be mindful of when it comes to process control and inputs and outputs? So that kind of respect for the process is a learning curve, and this is why I was excited to come to this conversation and talk about it.
Kirk, can you center a proposition for us?
Oh, God. I could center lots of things, probably not a preposition. I mean, proposition. Yeah. I mean, I really got interested and really didn't pay attention to binder jetting really until 2015, when, as we opened up the center then known as CADA to bring additive to the broader GE, we realized that, there was a significant use case for, production tooling for casting. And, so we had to get our hands on an X1 sand printing machine. Right. And, that's kind of where the light bulb started to go off. And, we used that for sand printing, but we also used that machine for composite tooling. We also used that machine for, N+1 other things that then kind of drew me closer to binder jetting. And since I spent many years sintering refractory metal powders after pressing them, then, the post-processing side is also very technically interesting.
Because your background is, you did a lot of sintering.
I did a lot of sintering.
Yeah.
At a very high temperature and very long time.
And just for my own street cred, next to my autographs SR71, this is actually an EB scatter diffraction of Ti-6-4 microstructure grown on an Arcam machine. So this is a gift from my staff at CSIRO, but I don't know how many people have titanium microstructure, actually additive manufactured microstructure. So, okay, why don't we go ahead and put that slide up, and then if we have the technology to do that.
Do we have the technology?
Great. So when I look at this, can you put it in slide?
I can try. Of course, all of the capabilities are hidden. How's that?
Beautiful. So I look at this and I see, the first thing that jumps out to me is the typical sintering, diagram with the necking and powder particle interaction. And fundamentally, to me, this speaks to me the principal difference between binder jetting and powder bed fusion, in that powder bed fusion is about weld pools in its basic sense, and so the need on the bed, if you will, is very different than the need on the bed for binder jetting and ultimately sintering. That's the thing that I see in this. Kirk, you can go last because it's your
because I invented this graphic. Yeah.
What do you see, Tyler?
So what I'm taking away from this slide is that the types of requirements that we put on the powder going into an LBP laser powder bed fusion space is very different than what we would typically care about for binder jetting. And understanding particle-to-particle interaction on a individual particle level is going to result in very different structures than you would in the binder jetting space than you would with powder bed fusion. And so we just typically undergo an entire phase change from solid to liquid in our melt pool track there. But in the case of binder jetting, we don't ever achieve that. And so there's a very different set of steps that have to occur to arrive at both a functional and as fully dense as possible part. And so having considerations for the feedstock and how they interact with each other, how you then can put them into the machine, how the machine's going to behave, and how all those factors result in a functional piece of hardware at the end of the day is far more complicated and different between the two. And we see that there with the theoretical sintering shrinkage with respect to basically how dense can you get your powder, but then you got to ask the question, how do you get your powder in the powder bed space and be that dense? So there's a bunch of mechanistic problems you got to overcome to getting powder to behave the way that you want it to optimize your binder jetting versus different constraints on the powder bed fusion space.
And I think you picked up on something there that that probably goes unnoticed. I would imagine most of the time, at least I don't hear people talk about it, but in binder jetting, it is a solid state affair. So the microstructure that you start with on the powder is still present in the sintered product, in some way, shape, or form. Whereas in powder bed, since you've remelted it, you've basically wiped out whatever history was there, and you're starting over again.
That's right.
And this means more things to some alloys and their compositional control, phase, content, et cetera, than it does in different alloy systems. I don't know. To me, as a materials, fundamental materials and process engineer, that's pretty cool when you think about the potential implications. It's a little bit like cold spray because the powder, you're not going through a melt, so therefore you're able to retain a phase composition.
Yeah, I'd say that, other than that you have to get to a very high temperature usually for sintering. So, the way I think about this problem is that, the requirements for sintering are usually the finest powder you could possibly get in order to reduce the temperature and time for sintering, right? And what do we all know about fine powder?
It loves.
It doesn't flow.
It loves moisture.
It loves moisture. It doesn't flow. It's tough to get and fill a bed with very fine powder.
That's right.
Yet, if we really want to sinter at a reasonable temperature and reasonable time, then we're going to use fine powder, right? So back in, from my history working with tungsten, we were using 1 micron tungsten powder, right, in order to be able to sinter to 95, 97% density, and that didn't flow, right? I mean, the molybdenum powder that I used to use, in a past life was the same. You could put it in a hopper with a 6-inch opening, right, and it would bridge the opening and stop flowing. So the kind of those sorts of things are really tough as you try and get something that works as a sintering solves a sintering problem. And so then many people think of, can you use a liquid phase? Can you add a low melting component or a surface component or a flow aid in binder jet to improve the binder jet process from a mechanistic standpoint, or the sintering process? And what happens, right? Then you have lots more opportunities for contamination.
That's right.
You guess you can add some magic pixie dust, but what does it do? It adds complications in a big way, right? The other thing I always think about is the classical sort of powder metallurgy problem, where in order to get really good compaction densities, in a classical die filling situation, you want a broad particle size distribution so that the boulders make the shape, right, and then the medium-sized powders fill in between the boulders, and then the fine powders fill in between the medium-sized powders, so you have a pretty high density before you compress it. The same thing here in binder jet, that would be great. However, broad particle size distributions also don't flow well, and then they make the driving force for sintering different, and you end up being at a much higher temperature for your sintering, or a much longer time. Right.
So lastly, Kirk, talk to us about, you've got 38% and 45%.
Right. So that's work from Li and Zhang at OSU, looking at a simulation of powder of different size and shape fractions randomly distributed in a bed at 38% density and 45% density. And if you look at the melt pool on the right for the 38% case, it looks like there's starting to be a balling defect. And you can see that in the cross-section view on the left, right? That the surface, melt surface, is really kind of cranky. And if you look at, if you increase the density of the randomly distributed particles to 45%, then you get a much, more uniform melt pool and a much more uniform surface topology. And so, again, this is simulation results from a couple of years ago, but I thought it was really nice to illustrate, compared to on the right-hand side, if you have a 45% bed density in binder jet, you're going to end up with 17% shrinkage. So, which is a very large number to accommodate, if you're thinking about making a 14-inch ring at the end, you need a 17-inch ring at the beginning. And then, lots of things happen in order to get that 17-inch shrinking down to, a 14-inch ring. So that comes with a whole host of other problems that we haven't even, talked about yet.
So that would strike me as an M&P engineer. I'm looking at this saying, okay, I have a requirement on powder bed processes to hit a minimum powder bed density of 45%.
Yep.
Beyond that, I probably don't care. It's just more work going into something that I'm probably destroying with laser gas
right.
flow interactions anyway.
Yep.
On the sintering side, on a binder jetting situation, or even with, I'll give our friend Arian at Hollow AM a mention. What kind of bed density are we looking at for binder jetting? Like a minimum, if we wanted to be so bold.
55. 65 would be fantastic, but it's usually hard to achieve.
I'm sorry, that's incorrect. The answer is it depends.
Oh, I didn't give the metallurgist answer.
Oh, no.
That is the tried and true M&P, answer for everything. Yeah, that makes sense. 55%, and that's a resultant. I think we need to be mindful that that's a resultant bed density, because the binder creates, it's got a ballistic effect on the bed.
Yep.
And a little bit, as we found out, highly flowing powders will then flow very easily once the binder hits it. So I see Paul came in with a question here. Thoughts on the hierarchy of porosity in the binder jet printed structure versus traditional powder metal porosity? Any reflections on that question? It's a well-structured question. Sorry, couldn't help myself.
It depends.
Next question, please.
Well, I think it's really going to come down to understanding the influence of the number of factors that go into the binder jet space. So with respect to the feedstock, how it's being distributed into the bed, which then interacts with the distribution of binder, which then, based off of how the powder particles are interacting amongst themselves, determines how good of infiltration you have by the binder. That can drive, if you have any kind of interlayer connectivity issues between individual voxels on a print versus, so that speaks to the interlayer porosity versus interparticle porosity. So it really depends on how well tuned and how well stress tested that process is to address some of the shortcomings that we maybe can have a bridge in terms of understanding from powder bed fusion to understand where we have just low energy defects versus high energy defects. Do we have just a delamination effect? And so in this case, it's, do we have a poor adhesion between our layers because our binder didn't quite make it all the way through? Are we blowing away the powder, like you said, in the ballistic case? So there are things that it depends. It really depends on how well tuned your process and your inputs, both types of feedstock, powder and binder, and then how well you then can adjust for those through subsequent steps of the process with respect to the debind and sintering stage. And then ultimately, how does that come out to be your shrinkage factor that we're talking about here? Can you adjust or control for that as best as possible through all the post-processing steps? So it really does depend.
I think what's what impacted me when I was fortunate enough to do that study with Carnegie Mellon and X1, with Dan Brunemer and people. When we looked at the results on the X-ray line, depending upon how you look at the results, one thing that was interesting is that you have a direct impact on the surface, no pun intended, but then you have basically a shearing impact at all the layers below it. So as that pressure wave or the pressure hits on those first couple particles, it then starts to impact all the particles below it for some, maybe 100 microns. The other thing that's simultaneously happening is when that fluid's coming in, it's displacing air, that's there. And it's easy to forget that there's that there's actually, a gas in the bed, which is, in this instance, if it's 55% dense, it's 45% gas. That gas has to be able to escape efficiently. Otherwise, you're going to create additional defects.
That's right.
Yeah. I mean, my perspective is if we're thinking and comparing binder jet traditional press and sinter, where, a traditional press and sinter, the range of particle sizes is, 1 or 5 to 150 microns. The resultant porosity is also, very, very different than if we're using, a pure metal binder jet with a D50 or a D90 of minus 22 microns, right? The largest particle pore size is going to be in the range of the largest particle. And so comparing a structure with many 150, 200 micron pores looks very different than a structure with a number of 10, 25 micron pores. If we're talking about more press and sinter with pure metals, not with the traditional PM materials, I think the same case happens, right? A lot of times, die filling and compaction has an influence on the distribution of porosity in a very different way than layer upon layer injection of powder and binder.
Maybe you can take the screen off so we can see each other a little bit bigger.
Yeah.
What role does we know in some instances there may be porosity in the powder particles themselves. Today I think we kind of shrug it off because there's enough noise in the system elsewhere that it's probably not contributing directly. But as we progress the technology and as we try to move into defect dominated performance like creep and fatigue, do we have an opinion about what that means? Is it significant?
I would say that it's significant in the sense that if you are not quite going fully liquid, then there's no good way to get rid of any kind of porosity that's present in particles to start with. Where as in the case with powder bed fusion, having experience with powders that are custom made that do have what we refer to as balloons, so these typically empty shells of a particle, you can
sound like it's just fun.
Oh yeah, you can try your best with however you're running your machine to hopefully consume those with repeated melts of the same region of your part as you're building past in multiple layers, that whatever kind of defect was present in the particle is consumed. But in the case of binder jetting, you don't have that opportunity. Nope. You can't consume that void because there's no thermal process until way later in actually forming the part. So, and you're never going to go molten enough, or you're never going to actually have enough energy to where that then actually disappears. So you do have the opportunity to kind of self-heal, as we would sometimes refer to in the powder bed fusion space. But sometimes if you have too many, your part then reflects it. But in the case of binder jetting, no, it's those things I would expect to hitch a ride and stick around, which is unfortunate. Yeah,
once a trap pour, always a trap pour, and just about. So I would completely agree. The impact of what powder we're using, though, is typically makes that, I think we should make that impact an order of magnitude less. Right, so the incidence of pores in gas atomized metal powder is really low until you get above 100 microns.
Right, that's right.
And so, if we're using D90 minus 22 powder for binder jet, for example, right, then our chances of having trap pores are pretty small. inside powder particles.
Yeah, I think it's one of the things I struggled with is, having both worked on the jet engine side as well as just, fatigue-driven static particles on aerostructures. It's putting defects exactly where I don't want them, which is just underneath the surface, which is very hard to find, and I would be, very difficult for me to, my minimal criteria for inspection is typically much bigger than those defects are.
Mm-hmm.
So that kind of moves on to another topic here, which is around standardization, and I know this is, Tyler, an area kind of near and dear to your heart. When we look at these processes, what does it mean to standards and standardization? I think having said this, we're certainly not picking on binder jetting. We all believe in it, and again, it's just like, maybe let's not make some of the mistakes that we made in powder bed fusion.
Right.
Right.
I could monologue for too long on this, so I will do my best to be as succinct as I can. The challenges we have with standardizing binder jetting are that the process, I would, at a very high qualitative level, would say is more complicated than powder bed fusion, in the sense that you have more factors that you have to have under control, or at least understand, so that you can properly implement and use the process. As a consequence of that, it's very difficult for a single document that would be released by some standards definition organization, an SDO, to publish, that's going to be useful in every use case or variation on that process. So we then try to do, okay, well, I'd rather not go to the route of being the lowest common denominator. So how do we make this the most useful? And so what we have to be mindful of is our powder specs have to, for binder jetting, have to be utilitarian enough to ensure quality in the sector or industry we care about. In this case, the one I'm working more on at the moment is aerospace. Certain quality requirements in terms of traceability and reporting of data is a given. But when it comes to strict limits and controls on, say, size distributions, we're less rigid. And we then basically look to the machine OEMs, who are doing a lot of the development work currently, to basically productize the process from end to end. So they have their qualified powder stream going into their machines with their binder as the secondary feedstock into their process with their sets of parameters, and outputting from that is a furnace cycle that they then control and have put a lot of effort in to develop, and out comes an advertised set of shrinkage, densification, mechanical properties, final chemistry. All of that information is one consistent unit. And so we can't have a document that is going to apply to an X1, to a DM, to an HP. So we have to be as flexible as possible in writing a standard that is structured to allow someone who's making parts from one of these machines, or asking of parts from one of these machines, to both know what's happening, have traceability, and most importantly, repeatability. So that's kind of where we are in standardization. Whereas with LPBF, the difference being is that the powders have been, in a sense, commoditized. There's a little bit more flexibility on interchangeability between the powders going in as a feedstock. Whereas with binder jetting, we expect that machine OEM who's developed the process is going to tell you got to use our blessed powder with these characteristics in order for everything else to work. And if you don't, you're running the risk of not getting the density you want, or you're going to have a different shrinkage, or you're not going to be successful at a print at all. So the standards have to reflect that amount of flexibility. And so we may end up having different documents that describe in a public space properties for different machine platforms that use the generic binder jetting process control framework, and then a fairly low bar, fairly lowest common denominator powder input. Really what you care about at the end of the day is the chemistry of the final product rather than the powder going in, because the process does affect the chemistry. But we're not going to tell people you got to be super tight and restrictive on these elements here, because in fact, someone's binder might change how much oxygen is present by stripping that away through the debind and sintering step. So we have to be mindful of this, whereas in the powder bed fusion, we want to be strictly controlling how much oxygen we have, because you pick it up, you make it worse as you go along. So we want guardrails in place to ensure we have good quality. binder jetting is a little bit of a different animal. So that's where it gets complicated and challenging to make everybody happy. And we know we're not making everybody happy. We're doing the best we can.
Yeah, it's like you said, it's a series of processes, not just
That's right.
a single process, because the binder itself is important for a variety of reasons. One is you want it to be there, and then you want it to go away completely.
That's right.
Hard.
Yep.
We want it to. It's opposing requirements, and then the printing, and then the sintering. And so, I think that's. I think it's a challenge, but it's, in many ways a fun challenge to go make that work. I know from the aerospace side of me, it makes me cringe to think about, putting a polymer on my powder. But, with enough testing, you overcome these things. We do have a good question, which is near and dear to my heart. In AM, we often hear that people talk about the perfect powder is the most spherical. And at least one company has the most spherical powders out there, which I think is interesting. We know now that this is often not true. What is the perfect powder for binder jet processing?
How about, why don't we answer the perfect powder for laser powder bed first?
Well,
that should be easier. That should be easier.
I think there's probably a couple different questions in there. Is it a powder? I'm mindful that our friends at Uniformity Labs just raised a bunch of money yesterday.
Yep.
And they have certainly an opinion and an approach which would strongly impact binder jetting. So the distribution, and I've often been thinking about, we tend to not think about morphology as being a component of bed density, but you can introduce different shapes and sizes into this equation. So it's a really three-dimensional problem. Yep. So perfect powder. Kirk, what's the perfect powder for? Is it spherical?
No. I mean, in my mind, the requirements are, right, flowable enough, fine enough to sinter, right? What else? A couple other requirements, but in my mind, the perfect powder ends up being something that's engineered. And so we look in ceramic processing in order to get perfect powders. A lot of times you'll take really fine powders that don't flow well, spray dry them to get something that's kind of agglomerated, right? And then engineer the size and shape of those agglomerates. Right? This is what's done with your Tide detergent, right? Those particles are not particles, right? They're engineered sums of many different components that then break up in the wash perfectly. Right? And we need to do something like this for the perfect binder jet. And so if you could get, sub-micron fine particles agglomerated in a way that you get that you have good enough flowability to get, and a wide range of agglomerate sizes to get great bed density, then we're talking a much easier to control process. So
your ideal is a engineered powder configured with the, I'll say, spreading or recoating of the powder. Those things have to work harmoniously.
Yep.
Tyler, do you have a perfect powder?
Yeah, I could speak to that a little bit.
You sit back on your back deck with your hands back, and the perfect powder comes along.
So I would say that I'm basically going to echo what Kirk has said, but I'll add a little bit of flavor from the standards world. We have historically written powder specs to make them easy to procure and easy to make. And so people have commonly expected these nice natural distributions that are resultant of the process. And so that's easy for someone like a powder producer to generate and then to provide as a product for an input to a process as feedstock. In the case of binder jetting and laser powder bed fusion, what comes out of these easy to procure and easy to define and well-bounded shapes and distributions may not always be the most ideal powder distribution, the shapes that are resultant of it. It's easy to make and it's easy to sell and easy to describe. So there is tolerance in powder bed fusion there's like a lot of margin on your powder. You basically are trying to go from the powder bed to liquid, and that's all you really have to manage with your laser. But in binder jetting, because of the particle-to-particle interaction, how the binder infiltrates, how the binder behaves upon impact, all of those characteristics have to be there's more attention that has to be paid to it. As a result of that, the engineering of the powder based on distribution, the tolerance to size, you could even, I understand that some of the machine OEMs are playing with water atomized powder, which is not something that is perfectly spherical and even in the most remote sense. So it's the right powder for your intended process and application. And there are ways to get around some of the technical problems, but there's no one perfect shape or one perfect distribution, because you got to turn the other knobs to match it to make it all work at the end of the day.
So I would say the perfect powder is consistent.
Yuck, yuck.
That's like it depends.
Qualifying. There you go.
Yeah.
But I'm not hugely. I've done a little bit of MIM work many years ago, but as I understand it, MIM powder typically they prefer it not to be spherical because they want the interlocking behavior. Do you guys have experience with MIM?
Me personally, no.
Yeah.
Yeah, so I mean, you get atomized powder, but it's atomized by usually typically a very different process. So either sprayed through a nozzle with a spray of water and then drying and solidifying in inert gas, or some other sort of modification of a typical inert gas atomized process that results in very fine powder. And they typically are not angular, but they're oddly shaped, non-uniform shape, and then what the MIM world usually qualifies to is the biggest size that's in the distribution. So like I was saying before, D90 minus 22 or D90 minus 16. So 90% of what you get is below a certain diameter.
Cool. So just a quick note to the audience. So if we don't get to the questions here, feel free to join us at the tables afterwards. I think we're all at a different table here, so I'm sure everybody will go to Tyler's table, but
please do ask him all the hard questions.
Ask him all the hard questions. That's what he signed up for.
I have another meeting I got to go to. See ya.
The other thing that's been upvoted here, I think there's a lot of good questions here from inspection and the centering, furnace atmosphere effects to design challenge. And so the design challenge to me is interesting because I think this is where I get frustrated is that I've had conversations with people that try to, compare powder bed to binder jetting, and I keep getting stuck like, why are we comparing these two things? I mean, a Ferrari is a good car and an F-150 is a good truck, but we don't often compare those. So, it's kind of that design space is different. What are your, do you have people asking you this question, Tyler, or how do you reflect on it?
So in the places that I've worked, people haven't asked questions about the design differences intended for binder jetting versus LPBF because people don't know the utility and the application space for binder jetting yet to have it on their radar. So the problem is coming from a different direction. So now I'm trying to educate, hey, there's actually a different process here that can get you the kinds of parts that I think you're wanting out of LPBF, but are running into problems in actual execution of that tool. Here's something else that can meet those requirements and give you the thing you're looking for in a different way. So it's more the instead of the pull by people asking, how do I use this tool? It's like, hey, no, here's something else you can go consider to make your parts a different way. And so that's more of me pushing in that direction and educating folks to give them the opportunity to make something different. But to the point about design differences, one of the best things that I have been trying when coming to educating folks about binder jetting is the lack of need to have the kinds of support structure that you commonly see in laser powder bed fusion, and the headaches that we run into so frequently on trying to both restrain parts in the laser powder bed fusion space or manage the amount of heat flux when you have part constrictions and things just want to heat up as a part of the process as you continue to build higher. Things that just can make your parts fail in the printer, or you get terrible distortion. So you don't have a lot of those same problems in the binder jetting space. And then further still, you can in some cases have parts that just float in space. And so you can then fill the build volume a lot more with certain kinds of parts based on the requirements of what those are. And pattern bed fusion, that's a lot harder of a problem to do if you have to figure out a way to support something in mid-space on your powder bed to continue building in the Z direction, or stack parts and then hope that part one is the same as part two, even though they're of the same design. Do they come out the same way because you're supporting them differently? Binder jetting doesn't have that problem. So that's where bringing people to the table, hey, you should really consider this because it gives you different solutions to those problems you're encountering now. That's typically where the education comes in.
Yeah, I think from well, we break it down into the sort of that design for additive and the modified for additive, and it does very much have different. It still has an MFAM piece to it. It is different, as you would expect, and because there are things you're dealing with. A couple of things happening at the same time. One is you're ejecting this binder down. There's a quick kind of curing step. The powder needs to be a certain temperature. Things are very kinetic, and that will drive some interesting propositions for you. I do want to kind of wrap up here a little bit. I think there's a good sintering furnace atmosphere. I got a couple of votes. That's a great Kirk question. Join his table for that.
It depends.
In terms of binder jetting, yeah, if they let you get away with that, that's great. Inspection. So Greg's got very good questions around inspection. I suspect some of those don't really have answers right now, given the relative infancy of binder jetting compared to some of the other techniques. Paul's been peppering us with really good questions. One is I would direct you to the last article that we did in AMT. We did kind of a quick process economics, looking back, a data-driven approach on a specific part that we designed, comparing it binder jetting and powder bed fusion, which was, again, it's not easy to find parts that are good for both processes. We did, but it's more than just the cost of the machine, and there's a little bit of the throughput, as Tyler's pointing out. You can nest parts and stack parts in binder jetting. The only problem with that is then you got to be prepared to do something with them. When they leave the printer, if they just sit around, that's not helpful either. So with that, I think we might just move to the tables, and this is something cool that we can do with the Remo platform. I want to remind everybody that in a month we will do a similar episode, but instead of me, you'll see Laura Eli talking about her favorite technology, directed energy deposition. And we also will be joining the AM Coalition at the end of the month to talk about Neighborhood 91. So look for us on that. Otherwise, there's no shortage of things going on. Thanks to both Tyler and Kirk for coming in, and our intent with this series is kind of, elevating or not elevating. That's a little bit arrogant. We highlight, individuals in the industry that we think, are doing the yeoman's work. So we like the technology piece, and we like the getting to the requirements. So Tyler, thank you very much for agreeing to participate. That 45 minutes just went very, very fast for me. So.
Yep. Right.
All right. We'll turn it over, and the magic of Remo, I guess, will put us at tables.